Shall we play a game?
Oh.
Many things come in threes. The number 3 isn't all that special. But what about a collection of 3 objects? Is there anything special about that? In fact, there is. This is the set N, consisting of the elements 1, 2, 3. We can define a function on this set from it to itself. What would such a function look like? Well, a one-to-one function maps every element to a unique output element assigned only to that input number. So consider a domain set in red consisting of 1, 2, 3 and a range set also consisting of the set 1, 2, 3. If we think about a mapping, a function that takes all of these elements to each of the elements in the range, we're creating a one-to-one function. Now essentially, this function produced what we call a permutation, that is, a rearrangement of the ordering of the objects in the set. The numbers 1, 2, 3 got mapped to the numbers 2, 3, 1. So in a sense, this function just rearranges the order of the numbers in our set. Considering this, a natural question might arise. Just how many one-to-one functions are there? Do you know? If you said 6, or 3 factorial, or 3 times 2 times 1, then you know something about counting arrangements. The number of one-to-one functions is the same as the number of possible arrangements, and the set of all one-to-one functions on this set is called S3, the symmetric group on 3 objects. But wait. What is a group? And what makes it so symmetric? We're going to attempt to answer this question now. Okay, so what is a group? If you have a set G that exhibits certain properties when you start putting the elements together from that set with a group operation, that's a binary operation such as addition, subtraction, division, multiplication, or maybe even composition. If you have this binary operation on the set of elements, you start defining what's called a group. So this will be the first requirement, that a set has a binary operation defined on it. Now, next we have to have an identity element in this set. So an identity element is an element that acts on another element and doesn't change it at all. Each element must have an inverse, or an element that undoes something, and this is going to lead to something called closure of the group. Finally, the group or the set must exhibit associativity under this binary operation. So let's organize S3 to construct it and see how it forms a group. Permutations. So to begin to construct the elements of our group S3, we start by identifying the identity function, or the identity element. That would be that takes the set 1, 2, 3 and maps it to itself in the same order, 1, 2, 3. The identity element will be given the designation E. Now the operation, our binary operation, is the act of permutation. So if we consider a different set of arrangements, we might consider the one that sends 1 to 2, 2 to 3, and 3 to 1, as in our previous example. In this example, the permutation, all elements get exchanged or rearranged. Now we might ask the question next, what happens when we apply this particular permutation a second time? We can denote that as alpha squared. So we perform alpha and then alpha again, and we get the permutation 3, 1, 2, a different permutation from alpha. Again, this one exchanges all three elements, and if I performed it one more time, say alpha cubed, we would return to the identity element. So there are no other copies of alpha that we could look for, and again, all elements were exchanged. Now amongst three objects, there's only two different ways you can rearrange all three objects. So then the next couple of permutations will fix one of the numbers. So let's call beta the permutation that fixes the number 1 and exchanges the numbers 2 and 3 in their order, giving us the permutation 1, 3, 2. If we had done this permutation again, it would return us back to the identity element, so b squared is e. And anytime you just switch two elements in a set, we call that a transposition. Now, combining alpha and beta together will give us another, permutation that fixes the number 3 and gives us the order 2, 1, 3. And finally, alpha squared combined with beta will give us the permutation 3, 2, 1, which fixes the number 2. So now we have all 6 possible outcomes, all 6 elements of our group. So S3 consists of the elements E, the identity element, alpha, alpha squared, beta, and alpha squared beta. Any other combinations of these elements will return an element that already exists. And that's because there's only 6 possible permutations. So, in fact, we found all the permutations, all 6 possible arrangements of the numbers 1, 2, 3. Because of this fact, we get closure, which means that any other combinations will give us elements that are still in the set. And for that reason, we could construct what's called a Cayley table for the group to show this closure. It's like a multiplication table for groups. And once you have a group with closure, you can do a lot with it. And this one constitutes something called a finite non-abelian group, because alpha beta does not always equal beta alpha. Order of composition matters. What about the symmetric part of the symmetric group? Well, we're going to have to answer this question with a little geometry. Since we have 3 elements, let's consider a 3-vertice polygon named as a triangle, with 1, 2, 3 as its vertices in a particular order. We notice what the permutation alpha will do to these vertices. 1 will get sent to the position 2, 2 to the position 3, and 3 to the position 1. So as a transformation, this would actually constitute a rotation of 120 degrees clockwise. So then we ask what alpha squared will do. It gives us the 3, 1, 2 permutation, which if we map where every number goes to, 1 goes to 3, 2 goes to 1, and 3 goes to 2, we see that this includes a rotation of 120 degrees in the counterclockwise direction, or the same as 240 degrees clockwise. And so those are the 2 rotational symmetries, as a third rotation would bring us back to the identity. So now beta is the permutation 1, 3, 2, and it fixes the number 1. And this would indicate for us a reflection over the diagonal 1, that is the diagonal that goes through the point 1, the fixed point. And that exchanges 2 and 3 through a reflection. We will see that the combinations of alpha beta as well as alpha squared beta will also be the other 2 reflections possible in our triangle. The permutation that fixes 3 will exchange 1 and 2, and alpha squared beta fixes the number 2, so the line of reflection goes through the point 2. pretty miraculous how permutations, rearranging of numbers, actually constitutes geometric transformation. This exhibits reflectional and rotational symmetry. And if we consider the identity element E, that doesn't change the order of the vertices, and that would be the same thing as a translation. So S3 is a group, and it exhibits geometric symmetry. Now there's one last property about the permutations and their connection to functions that can really be exploited, and something called Galois theory does just that. It makes connections between one-to-one functions, or isomorphisms, and the symmetry of transformations. Those are the congruence transformations known as isometries. These are the rigid motions in space. Now, to get to the heart of what Galois theory attempts to talk about is how there's a connection to the solutions to polynomial equations. So consider a polynomial function of the form f of x is equal to an x to the n plus an minus 1 x to the n minus 1 all the way down to a sub 0. Now, a polynomial equation, f of x equal to 0, will have a number of solutions, and if it's an nth degree polynomial, it'll have at most n roots. So in factored form, this function can be written as a constant times all the factors x minus a root, and all the roots that are possible, well, that would be n number of roots at most. So every nth degree polynomial can be factored in this form. Now, one key observation here is that the equation remains the same if you permute the roots. That is, if you exchange the order of the roots. So that would look something like this, where I'm just changing the order in which I'm writing the factors, i.e. the order of the roots. And because of the commutative property of multiplication, this does not change the value of the function. So there's a symmetry to the roots of a polynomial equation. It leaves it invariant. And I'll leave it at that. So polynomial equations have roots that exhibit geometric symmetry. And that's not exactly obvious. I leave you with a few questions for you to attempt. 1. Find all the elements for the symmetric group S4. 2. Can you generate all of the possible rigid motions, that is, possible congruence transformations for a square? Call this set D4. Can you show that D4 is a group? And finally, is D4 exactly S4 or a subgroup of S4? Good luck in answering these questions, and I hope you enjoyed this video. Please hit that like, subscribe, and notification bell for more videos. And stay tuned.